have studied how each term behave separately, R, L, and C. It is now time to put everything together. Okay, we're going to put all three elements together to form what's called an LRC or RLC circuit, putting everything in series. Alright, so here is the drawing. Okay, resistor, inductor, and capacitor powered by the same EMF. Obviously, when I apply Kirchhoff's rule, I get two equations. One is all these currents are the same. IR, IL, and IC. They're all the same, right? We call it I. It's a function of time. Okay. V, the potential EMF provided by the power supply, is divided among these three elements, VR, VL, and VC. So you get V, which is also a function of time, equals VR plus VL plus VC. Okay. Take a close look at these three voltages. Okay, we have studied them separately before. For a resistor, VR and the current going through it have the same phase. It is in phase with the current. Okay, VL, as you know, VL always leads the current by 90 degrees, right? We've studied that just a minute ago. Okay, so if I use this guy as a reference, then that one will lead by 90 degrees. What about VC? VC lags the current by 90 degrees. Okay, so again, using VR as a reference, you find VC is ahead by 90 degrees, VL is ahead by 90 degrees, and VC is behind by 90 degrees. So you're adding three functions with different phases. This is something new we have to deal with. Okay, you're adding three sine functions up. These three sine functions have the same angular frequency omega, but they do not have the same phase. Okay, if this is a sine function, then this one is a cosine function, and this one would be a negative cosine function. Okay, so then we may have encountered some difficulty trying to add these functions together because they don't have the same phase, sine and cosine. So how do we deal with that? How does one deal with quantities with different phase? Actually, not only different phase, but something that makes things easier. They have different phase, but they have the same angular frequency. Okay, same angular frequency. Now, you'll notice that when we studied simple harmonic motion in physics 1b, you recall that when we studied simple harmonic motion, we also noticed that there is a relationship between simple harmonic motion and uniform circular motion. Right? In what sense? Well, in the sense that if you were to draw a circle, okay, you were to draw a circle of a certain amplitude, okay, certain amplitude A. The amplitude is A, and this angle is, and this angle varies with time. Okay, so as this object moves in a circle radius r about 0.0, okay, with an angular speed omega, starting from a certain location, starting from this point, going up this way, then this angle, of course, is omega t at a time t, right? And as this point, okay, as this red dot moves in a uniform circular motion, the shadow dropped by this red dot on the x-axis will go back and forth, and that is a simple harmonic motion, right? Because x is equal to a times what? Cosine omega t. See, simple harmonic. As a matter of fact, even the y direction, look at the shadow in the y direction, you have y equals a sine omega t. That is also a simple harmonic oscillation. So you see, I can get a simple harmonic oscillator by looking at, first of all, a dot doing uniform circular motion, and then project that dot as a shadow onto either the x-axis or the y-axis. Okay. Now, instead of this dot, I can also consider this vector. A vector starting from O, pointing towards that dot. So this vector would then rotate with an angular speed omega. The shadow of this vector, or the x component of this vector, and the y component of this vector, are both sine cosine functions, changing with time like that. Okay. Now, in our case, what can we get from this analysis? See, we're looking for these real life quantities, the current, VR, VL, VC. These are all sine and cosine functions. By the way, I can always turn a sine function into cosine function and vice versa by adding or subtract 90 degrees. So therefore, I'm going to just say everything is a sine function, okay? Just for simplicity, I don't have to deal with cosine functions. So everything is a sine function. So we're trying to add these different sine functions up. They have the same omega, but they do not have the same phase. Okay, they have phase differences. Adding them up is not directly so simple if you try to do this, with trigonometry. However, you'll notice that these sine functions can be thought of as what? As the y component of this vector A. See that? Right? And if you want to add the y components up, why don't you add the vectors up first? So you got two vectors, A1 and A2. You add their vectors up, all right? And then say you get A1 and A2, add them up, you get A, right? The y component of A shouldn't have equal to the y component of A1 plus the y component of A2, right? Okay, so that is the idea. So what we're going to do is we're going to introduce something called a phasor. Okay, it's called a phasor. It is a vector, something we define. It's defined such that this phasor vector starts from the origin of a coordinate system and it turns with an angular speed omega as time passes by, okay? Turns with an angular speed omega. It has x component and y component. Okay, I use the x component as a reference line, and the y component, of course, is then ay equals a times what? Sine of this angle, which is omega t plus phi initial. I can always add enough phi initial if I want to. Sine omega t plus phi initial. Now, then with this phasor, all of these quantities, all of these sine functions can be thought of as the y component of that phasor, right? And what I'm doing here is I'm trying to add all these y components up, right? But if a vector A equals the sum of a whole bunch of vectors, then isn't it true that x components added up would be equal to the x component of the resultant vector, and the sum of the y components will equal to the resultant y component, right? I'm looking for this. This is the sum of all these y components, and it is also equal to the y component of the resultant vector. See that? So the idea is I'm going to define a phasor, which is a vector, in association with each of these real quantities, which of course are not vectors, they're scalars, such that each of these quantities is the y component of such a phasor. Now that phasor behaves very simply. It simply turns around and around with the same angular frequency omega. And if I want to add these y components up, all I have to do is add these phasors up first, vectorially. And then let me find the y component of the resultant vector, and that is the sum of all these components. Okay, and this job can be made really simple in our case, because after all these phasors will turn with the exact same angular speed, meaning that the angle between each two phasors will never change. The entire phasor diagram will turn as a rigid structure. Okay, so again, all the phasors in our AC circuit have the same omega, so they rotate together in a rigid structure, adding two phasors together. So with that in mind, let's try to add two phasors together. I get A1 and A2, right? Two phasors. Again, the meaning of A1 and A2 is that if you like A1, that the y component of A1 corresponds to a real physical quantity, which is a sine function of time, okay? And the y component of A2, or A2y, is the real physical quantity, which also varies as a sine function of time. Now, my job is to try to add these two y components up, which is hard to do because they don't have the same phase. So what I'm going to do now is I'm going to add the two phasors up first. I'm going to add the two vectors first. Okay, so that's what I'm going to do. And I'll get the resultant phasor. Okay, I get a resultant phasor, which is A1, vector A1 plus vector A2. Right? That's A, which is equal to A1 plus A2. And what's so special about this resultant vector? The y component of this resultant vector, ay, is ay1 plus ay2. Okay, so with that, I'm able to find the sum of these two sine functions with different phase but the same omega. And this job can be done relatively easily because, again, the angle between A1 and A2 never changes. The whole thing turns with the same exact angular speed. It's a rigid structure. Okay, both of these vectors along with the resultant vector will turn, but they turn at the same rate, and therefore the angle between them will never change. Alright, so that is the idea. I'm going to define a phasor in association with each of these quantities, such as the current, such as the VR, VC, VL, and so on. Okay, and then instead of adding the V's together, I'm just going to add their phasors, their corresponding phasors together, and see what is the net resultant phasor, and from that resultant phasor I can find, the resultant V and whatever that comes with it. All right, so now we can study RLC series circuit with phasor method. I am going to, first of all, I'm going to power the circuit with this given EMF. Okay, this has to be given, because if the EMF is not fixed, of course I don't know what the circuit would behave. I have to power it with a given EMF, which is the one we wrote before. V maximum, that's the amplitude, sine omega t. Okay, and here is the resultant current. The current is the same, going through all three elements, but you have to realize that it may not have the exact same phase as the voltage anymore, as the EMF anymore, because this is not, in general, a purely resistive circuit. Otherwise, phi would be equal to 0. Okay, so you can imagine that the resultant current will have the same omega, but it will not necessarily have the same phase. So I'm going to write omega t minus phi. Okay, so I'm going to assume that the current lags behind V, the EMF, by an angle phi. Of course, it doesn't have to be lagging behind. If phi turns out to be negative, that means the current actually leads the voltage, leads the EMF by an angle phi. Okay, so that's the common current going through all the three elements. The question is, how do we find the resultant amplitude of the current and the resultant phase lag between the current and the EMF from the power source and from the parameters of the circuit, such as R, L, and C? Of course, these quantities are determined by Vt and by R, L, and C, but how do you find these quantities? Again, the idea is I'm going to introduce a phasor for each of these quantities, Vi, Vr, Vl, and Vc. Okay, and since by Kirchhoff's rule, the EMF, the voltage across the EMF, equals to the sum of these three voltages, right? Then, instead of dealing with these quantities directly, these functions, sine functions directly, I am going to add the phasors representing Vr, Vl, and Vc. That should be equal to the phasor corresponding to V. Okay, once I get that, once I write this expression, I'll be able to graphically obtain the magnitude of the current and the phase angle. We'll do that. Okay, now again, before we draw such a graph, okay, let's review the phase differences. Okay, the voltage in the EMF is like this. It leads the current phasor by an angle phi. You see, because the current phasor is an angle phi behind it. See this negative sign here? Phi is not known yet. We're going to solve it. Okay, we're going to try to solve it. VR has the same phase as the current I. So I'm using the current I, using the phase of the current phasor as a reference. Okay, with that reference, VL, the total EMF, leads by phi. VR has a phase angle of 0 relative to the current phasor, has the same phase. VL leads the current phasor by 90 degrees, and VC lags behind by 90 degrees. Okay, keep these in mind. Okay, now we are going to draw the phasor diagram. Okay, we're going to solve this problem graphically. Okay, you'll find this very visual and elegant way of solving the problem without having to add a whole bunch of sine cosine functions together algebraically. This is our reference line. I'm going to draw a phasor first for the current. Okay, this current phasor, using this reference line, the angle is omega t minus phi, right? The amplitude of this, or the length of this vector, is I maximum. The y component of that phasor is the actual current, which is I maximum times sine of omega t minus phi. Okay, that's the expression that we know should be true for the current. Now, as time goes by, this current phasor turns around with an angular speed omega. Okay, what I'm going to do is I'm going to introduce the other phasors for actually all these phasors for the voltages. Okay, first of all, VR. VR has the same phase angle as the current phasor. Okay, so I'm going to draw VR now. I'm going to draw VR now in the same direction. Okay, in the same direction as the current phasor. So here is VR. Okay, the current. Here's the voltage phasor across the resistor. Now, what about VL? VL, remember, VL leads the current phasor by 90 degrees. Okay, this is the positive direction of turning. So if I, at this moment, I points this way, then the phasor for VL should point that way, 90 degrees ahead, 90 degrees that way. Okay, so that is what I'm going to draw. Here is the phasor for VL, 90 degrees. VL phasor. Okay, now what about the VC phasor? VC phasor. VC lags behind the current by 90 degrees, while VL leads by 90 degrees. So basically, VC is 180 degrees away from VL, right? It goes back. It goes back way by 90 degrees. So I'm going to draw that now. Okay, I'm going to draw a VC phasor. I'm trying to use a different color. Okay. Here's the VC phasor. By the way, the length of this vector is the amplitude of the voltage across the inductor, and that is omega times L times I maximum. Remember that. And what about VC? The length or the magnitude of this vector would be I maximum times omega times L. I'm sorry, times omega times C. Remember? Okay. And this vector VR should be I maximum times R, of course, Ohm's law. Okay. What do we do now? We have VR, VL, VC of all three phasors, right? And the idea was, instead of adding their y components up, I'm going to add these phasors up first, vectorially, and to find the total resultant phasor, and then we go from there. Okay, now how do you add these three vectors up? VL, VR, and VC. Well, first thing you notice that VL and VC are in opposite directions. Okay, so it's easy to add them up first. Depending on which one is longer, you will get a net vector out of these two in the direction of the vector that is longer. The way I draw it, VL is longer than VC. This sometimes happens, and if that happens, we say the inductor obviously is more important than the capacitor because it produces a greater voltage drop. Then we say this is an inductive circuit. Okay, an inductive circuit. And this happens if VL is greater than VC. Okay, VL is greater. The amplitude of VL is greater than the amplitude of VC. And as a result, when you add these two vectors, you're going to get a resultant vector going that way. Right? Going that way. This vector has a magnitude which is VL minus VC. Okay, VL minus VC. So I'm going to write VL minus VC as far as the magnitude is concerned. Now I'm going to combine with VR. Right? So here's how I combine with VR. Right? This, in fact, is a very simple rectangle. So you add them all together, you get this red vector. This red vector is the sum of VR, VL, and VC. What do you think that is? Well, go back to the previous page if you don't remember that. The sum of these three vectors is what? Is the phasor for V, or the EMF. Okay, so this is V, the phasor for the EMF. And because we know what that phasor is, that phasor should have a length of V maximum, should make an angle of what? Omega t with the reference line. How do we know that? Because that's how we defined VT. See? V maximum sine omega t. Alright, so the y component of this vector shouldn't be V maximum times sine omega t. That's what this angle is omega t. This angle is omega t. But wait a minute, that angle is omega t minus phi, so what do you think this angle is? Shouldn't that be phi then? In fact, this is completely understandable because look, here's the current phasor and here is the EMF phasor, right? There is a phase difference between the EMF and the current. The phase angle is phi, and since everything turns this way and the current is here and the voltage is, the EMF is there, you know, the current lags behind by phi. Okay, that's why I used negative phi for the phase angle relative to V. Okay, so my job is to find what? The amplitude of the current and this phase angle. Okay, that's what I want to find. Now, look at this right angle triangle here. I can use Pythagorean theorem to relate the magnitude of three sides, right? The magnitude of the hypotenuse is the amplitude of the EMF, and that is V maximum. So V maximum squared must be equal to what? This length squared plus that length squared. What is this length squared? That is the amplitude squared for the voltage across the resistor, and that is I maximum R squared, right? Okay, next I have to add to that length squared. VO minus VC. VO is the amplitude of this vector. Okay, VO is the amplitude of this vector. What is the amplitude of this vector? It is I maximum times XL. We know XL is, it's omega times L. Okay, and then minus BC, the amplitude of that vector, which is I maximum times XC. XC, by the way, equals 1 over omega C. Okay, so you square this, right? And you notice that there is I maximum here, I maximum here. Everything else is known. I can actually solve for I maximum by taking out this common factor. I maximum, therefore, equals to, don't forget you have to square it because everything is squared here. It's V maximum, right, divided by what? Square root of R squared plus XL minus XC squared. Now I know what XL is, it's omega L, and I know what XC is, 1 over omega C, so I can write this as, one step further, as V maximum square root of R squared plus omega L minus 1 over omega C, then squared. Okay, this is the first important result that I obtained with the help of the phasor method. Without going through too much trouble mathematically, all I really did was I graphically added these vectors up and used the Pythagorean theorem. I found what? I found the amplitude of the current in the LRC series AC circuit. It is proportional to the amplitude of the EMF that powers the circuit. That makes sense. And it depends on R, L, and C in this manner. Okay, in this manner. We're going to come back to discuss this result more carefully later. But at this point, let us also don't forget that we need to study the phase angle phi. This phase angle phi. How do you find the phase angle phi? Okay, I don't want to lose this phasor diagram. Look, once again, from this right angle triangle, I know that tangent phi, okay, equals what? This length over that length, which is VL minus VC divided by VR. VL is the amplitude of the VL phasor, which is omega L times I maximum. And then minus VC, that is I maximum over omega C. And then I divide it by VR, which is I maximum times R. See, you can cross out all the I maximum. So I get tangent phi equals 2. All right. Omega L minus 1 over omega C divided by R. This is the phase angle. The phase angle between the EMF and the resultant current in a circuit. Okay, the current lags behind the EMF with an angle phi. Of course, if angle phi is negative, that means the current actually leads the EMF.